Good morning, my YouTube viewers. It's Crystal here. I just wanted to do another code review. I'm going to do this code review on the Boston house prices, and I'm going to use linear activation on a sequential neural network with Tensorflow. And so I decided to use Boston house prices because it's falling out of popularity. And the reason why is because of some of the features that are actually in the data set. For example, here, B means the percentage of blacks in the town, and people don't like that, understandably. And LSTAT is lower status of the population. So I don't know if that means people of a lower status. I'm not sure exactly. But because of the B, definitely people don't want to use the Boston house prices. So I thought, well, I'll go ahead and use the Boston house prices before it gets taken off the internet, because at some point the people who, shall we say, the woke brigade are going to want to take this off the internet. So this is an old data set, I think back from the 1980s, maybe even earlier. And that's why it has the features that it has. It certainly wouldn't be there today. I'm not sure what they do in Boston, but it surely wouldn't be there today. So what I did was I created this program in Google Colab, which is a great platform. It's a free online Jupyter notebook, and so I created the program in that. And the only bad thing about Google Colab is the fact that it doesn't have a very good undo function. So you need to be very careful not to accidentally delete or overwrite any valuable code, because you might not get it back. But one thing that you can do, you can come over here to all save changes, and then that will give you some information about the program. And as you can see, whenever I made the program, I did it all in one setting yesterday. And since I did it all in one setting yesterday, you've got the original program, but you don't have the save program. So let's say if I hypothetically deleted any code, I wouldn't be able to get it back. But I just wanted to show you how you can try to get your code back if you accidentally overwrite it or delete it. So after I've created the program, then what I want to do is I want to import my libraries. So the libraries that we're going to import are Pandas as PT, which creates the data frames and series and also does data processing. NumPy as NP, which it creates NumPy arrays and numerical computation. We want to import in the program sklearn, which provides machine learning functionality. We're going to import TensorFlow, which is your deep learning and your neural networks. Then we're going to import matplotlib.pyplot SPLT, which is your graphics visualization of the data. And then we're going to import Seaborn as SNS, which is also graphic visualization. So after we've imported the libraries, then what we're going to do is we're going to read in the data set. And so I've taken the data set from Jason Brownlee's GitHub account, and I've used that. But the only thing about Jason Brownlee's GitHub account is the fact that he didn't have the column names in the data set. And because he didn't have the column names in the data set, it was a little bit difficult to use. So I had to go someplace, look on the internet to see if I could actually find the column names of the Boston house pricing data set. So I put the column names in myself under df columns equals, and then that gave me all the column names. But if you're just going to use Jason Brownlee's data set, it doesn't have the column names. So you can see these are all the columns. And fortunately, all of the features or columns are numeric, so that means we don't have to encode anything, so that's good. And MEDB is your target variable, and everything else is your features. So we're going to describe it. So we're going to describe it so you can see the vital statistics of every column in the data set. You've got a count, which is interesting because it's 506 rows of data, but if you have any null values, then that will be reflected in the count. So that's one way that you can look and see if you have null values, but I go another way. Then you have the mean, the standard deviation, the minimum, the 25%, the 50%, the 75%, and the maximum. So now we're going to do df.info to find out some more information about this data set, and you can see that all of the columns of data are numeric because they're either floats or integers. So that's good. So you don't have anything to impute. Now what we're going to do is we're going to look and see if we have any null values. We don't have any null values, so that's good. So we don't have to deal with null values. Now we're going to analyze the data frame. So we want to see how many unique values are in each column of data. So you have 4 column in df, print call, df call, and unique. And then so you can see all of the different number of unique values for each column of data. And so if it has only a few unique values like Chaz, you can check, you can find out what the 2 indicators where Chaz are, or RAID is 9 or tax is 66. So let's see what Chaz says. Charles River Dummer variable 1 if track bounds river 0 otherwise. So that just says, so that's one thing that you can do if you want to find out the percentage. So you've got CRIM 504, ZN 26, INDA 76, CHAS 2, NOx 81, RM 446, age 356, DIST 412, RAID 9, TAC 66, PT ratio 46, B 357, LSTAT 455, and MEDB 229. So what we could have done is, like for RAID, I don't know what RAID means. Index of accessibility to radial highways. What you could have done is, if you had anything that was an object, you could have made a pie chart out of that, but we don't have anything that's an object. And pie charts are a little bit more difficult to make. So now what we're going to do is we're going to check the target value, which is MEDB, which is median value of the house. So you can see this is the target value. And then you do have like what looks like a bit of an outlier because you've got some houses valued at 50,000 pounds or dollars. Now we're going to do a value counts because we want to see how many values only appear once, because if a value only appears once, you're not going to be able to adequately make a prediction on it, because you need to have it needs to appear more than once for you to be able to make a prediction. So what I do is I remove all of the rows of data where the value appears only once. So instead of having 506 rows of data, now we only have 406 rows of data, because you have 100 rows of data where the value appears only once. So if it appears only once, there's no point even having it in the data set because you need it to appear twice. And then in addition to that, I think you're going to have a hard time using train test split if it appears only once as well. So now we look at it again. We do a histogram of it again, so you can see here that the histogram is a lot different shape because we've gotten rid of 100 rows of data. But you've still got that outlier there. You've still got quite a few houses of $50,000. So now what we're going to do is we're going to do a scatter plot of, if you know how to read scatter plots, of the lower stats. So lower status and how it affects the median value of the house. So I think the less lower status you have, the higher the median value of the house. That's what it looks like. And now we're going to look at the number of rooms in the house. So you can see the number of rooms in the house sort of like settles around 5 or 6 or 7. But the more number of rooms you have in the house, the higher the value of the house is going to tend to be as well, for the most part. So now we're going to make a heat map, so you can see how the columns of data, how they correlate to each other, and you can see tax and RAD seems to have a high correlation. But what I decided to do, I decided not to remove any columns of data, and the reason why is because it's not got a large amount of columns anyway. But if I had a lot of columns of data, then what I would do is I would remove the columns of data that had a high correlation to each other just to reduce the features. So now what we're going to do is we're going to define our x and our y variables. So y equals df.popmed. So what that does is that just takes MEDV out of the data frame. And then you say x equals df. So MEDV has been taken out. So now what we do is we're going to use sklearn to split the data set up into training and validation sets. So xval, xtrain xval, ytrain yval equals train test split, xy test size equals 0.1, random state equals 42, and then you can check the sizes of your data frame. So it's important to check the sizes of the data frame to make sure that you haven't made a mistake somewhere. So now we're getting into the Tensorflow side of the program. So we want to import all of the functions, the libraries and the functions dealing with TensorFlow. And you can see in this one we're using TensorFlow 2.12. So now what we want to do is we want to standardize the data. So we're going to use the normalization function to create an extra layer. So normalizer equals normalization, axis equals -1, normalizer.adapt, np.array xtrain, print normalizer.mean.numpy. So that gives you the normalized data of all of the columns in the data in xtrain. So now what you can do is you can just do a comparison check. You can check to see what the first row of data is when it hasn't been normalized, and then you can check to see what it is after it's been normalized. And so this is interesting here because I didn't put a normalization in there. So that's something that I'm going to need to do. So we'll just say normalizer. So let's try it, see what happens. And then since I'm changing it anyway, we don't need the model because the model is if it's functional. So we'll look and see what it was without normalization. And without normalization, MAE was 4.12 and RMSC was 6.18. And let's just try it. So MAE was 4.12 and RMSC was 6.18. So since we forgot to put a normalizer in there, I think that's gonna so we're gonna try to use the normalizer again. So it worked, and so now you can see already that the MIE is reduced now that the data has been normalized. It's been reduced since the data's been normalized. So that's good. So that's why you normalize the data, to get a better level of accuracy. So yeah, our root mean squared error is much better as well. So that really improved the model. When we put the normalizer in there. We've got a lower MSE and a lower root mean squared error. And so we use the linear activation model. And one thing about Tensorflow is if you don't name the activation model, then it's going to automatically be linear. But we put linear in here anyway. So you're going to want to use linear activation model with a regression. But if we hadn't said linear, then what would have happened? It would have selected linear anyway, because linear is your default. So now what we do is we compile the model, and we've got optimizer equals RMS prop, loss is MSC, and metrics is MAE. We set up early stopping. So what early stopping does is if the loss after so many iterations or epochs, if the loss doesn't change, then it'll get out of the function, so it will early stop. And then we also check MC, which is model checkpoint. And then what we do is we train the data. So history equals model.fit, x train, y train, batch equals 32. So you want your batches to be 32. Epochs equals 500. Validation equals xval, yval. And then you've got your callbacks is early stopping and MC. You can see that it stopped early at 124, and it had an MAE of 2.7 with the val MAE. So your MAE improved and your RMSE improved. And the reason why is because you want your error to be as low as possible. So we've got our results when we evaluated the model, and the results was 2.7414. And then I created a graph to plot the loss and the MAE. So the loss and the valve loss is the blue and the green, so you can see that the val loss is a little bit more than the train data, and the MAE and the val MAE is almost the same. So you can see how the model performs with that graph. So now what we do is we find ypred. Ypred equals model.predict xval. Ypred equals NP around ypred, comma 1. Ypred equals ypred flattened, so we flatten it, and then you've got your ypred. And then what we do is we check our RMSE because it's root mean squared error. If you have RMSE is false, then it's root mean squared error. So we have a 4.04 RMSE, which is good. It's better than what we previously had. And now what we do is we have a graph where we're going to plot the true values against the predicted values. And so there's your true values against your predicted values. And then what we have here is we have a data frame where you can compare the actual values against the predicted values to see how well the model performed. And that's it. That's it for this code review. I've covered all of the pertinent details. I just wanted to do the Boston house prices because that data set is probably going to be taken off the internet at some point because of the type of columns that they have. So I thought, oh, well, I better get in there and get this done quick before we lose it. And I did use Jason Brownlee's data set, but on the data set that he had, he didn't name the columns. So I had to go someplace on the internet and actually locate the columns. So what we did in this code review, we found out that I hadn't put normalizer in the code review. So we put normalizer in the code review. And then we found that the error improved with normalizer. So that's why you actually want to use normalizer, is to improve the error. So I'm going to go ahead and close this video since I've done everything that I said I was going to do. So I would like to thank all of my subscribers for supporting my channel. If you like this video, please like, subscribe, and share. If you want to be notified whenever I make a new video, then please tap onto the bell button next to the subscribe button, and you will be notified whenever I make a new video. And thank you so much for watching my code review. I look forward to making more code reviews for you in the future.